Assalamualaikum. We are from section 2, group number 4. So the title of our project is Car Manufacturing Factory. So my group members is Muhammad Faris bin Nordin, and me Muhammad Fahmi bin Norawan, Muhammad Rashad Uzaini bin Azmi, Muhammad Luqman Hafiz bin Rosli, Muhammad Azizi Aswad bin Hisham, and Nur Azmi binti Azhar. So for the introduction, the consumption of energy in Malaysia has grown in recent decades. The increasing consumption of electricity by Malaysians reflects the growing affluence of the country. Plant distribution system design is essential for determining the many type of plant distribution network as well as their power consumption and transformer sizing. Industrial application features are generally focused on motor loads, reducing downtime and a variety of operation. Next, for the problem statement, to transform Malaysia into a modern country in the future, the industrial sector must be prioritized. One of the most serious issues is the explosion and heavy disaster produced by improper plant planning. The improper transformer size then causes the system to fail. Next, the power supply may be insufficient due to incorrect plant planning in relation to the power demand, resulting in energy waste as well as increased bill costs. Next, for the objective, there is 3 objectives of our project. The first one is propose a sustainable network design for the installation segment that include the entire expected power consumption and overall power factor demand by using Microsoft Excel. Second one is create a single line diagram for an industrial installation that indicate the main distribution transformer and suitable installation procedure. The last one is simulate the sketch industrial power network by using ETAP software. That's all for me.
Okay, next for the methodology, this project is to determine the proper industrial distribution, transformer sizing, and transformer rating for the car automotive manufacturing factory. So first of all, for the input parameter, we choose the potential industrial system, which is a car automotive manufacturing factory. Then we all load data for feeder 1, feeder 2 and feeder 3. Then for the process input, we define KU, KS1, KS2 and KS3 for all feeder, which is in Excel, Microsoft Excel. Then we calculate the total KVA for all feeder. Then the transformer rating must fulfill 2 criteria, which is the criteria 1, the maximum demand for industrial loading must be below than 65% of transformer full load size. And for the criteria 2, the voltage drop due to the largest motor starting at secondary must less than 10%. And for the output parameter, we need to display transformer sizing based on these 2 criteria and present a commercial Microsoft Excel tools in determining the transformer sizing, and present and run an industrial simulation network on ETAP software, which is for the normal load analysis and for the fault analysis. Okay, next for the methodology is used to determine the total maximum demands in Microsoft Excel. So to identify the proper transformer sizing for our car automotive manufacturing factory, we decided to divide 3 feeder, which are fabrication lines, assembly line and also the painting lines. All the parameter are given is used to calculate all the calculation for value of K, absolute load, operating load, peak load and also the reactive power using the formula that given in the project instructions. Then to calculate the maximum demand, the suitable utilization factor, which is KU, and also the diversity factor KS1, KS2 and also KS3 for each loads are identified by considering the duration of the operating loads in the factory. For example, the heavy machine like the welding machine A, welding machine B and also welding machine C and also for the heavy conveyor motor C, conveyor motor A, and also conveyor motor B. We are decided the suitable diversity factor is at 0.9. So then by multiplying the KS3 with the sub-plant distribution board SPDB, so our total KVA sub main generation distribution board SMGDB is 2540.61 kVA. Okay, next for the identify the transformer rating and also the voltage drop. So to fulfill the transformer rating, the criterion 1 sets the rated power of full load current kVA must be 65%. So this is the total kVA for all the transformer distribution, and we all select the transformer rating selection with the suitable based on the rated power at 65% of full load current kVA. So also for the voltage drops, we all can identify which is can fulfill the criteria 2, which is the largest motor starting at secondary must be less than 10%. So for the all transformers, you can see 2.09, 1.72, 1.49, 3.57 and also 2.23 are all less than 10%.
My name is Faris Minuddin. My metric number DE 180191. So today I'll be presenting about the part methodology and part simulation. So the transformer rating and voltage drop my friend was taught before. So I will explain for operating load, peak load and design load. For the operating load, we get the 3505 watt. For peak load, which is 1752. For design load is 2103. For the kVA, operating load is 2893, peak load is 3043, for the design load is 3352. For kVA, for operating load is 1830, for the operating load is 2487. For the design load is 2670. So this value will get the value from the maximum demand here. Below here, we can get the value of the design operating load, design load and peak load. So now I proceed to the design issues and solution. So basically, this generator already put before the issues apply. So basically, if the TNB breakdown, we can see here. I open the circuit breaker to show you how the load not function if the TNB problem or the TNB breakdown. So basically, if we open this circuit breaker, 3 circuit breaker, and also do not have any generator, so basically all the car manufacturing factory do not have any supply, so the load will become not continue to their manufacture or product. So the solution is I put the generator for each feeder, which is feeder 1, feeder 2 and feeder 3. Each feeder we put the one generator only here. So for the specification, I will put the specification parameter at the full report. Okay, now I will proceed to the simulation part, which is demo simulation. I will explain about the first power flow analysis, second is for analysis, and the 3 is issues, design and solution. So this is for the singular diagram for car manufacturing factory. So this supply from TNB, this is for the SMGDB, So this is for the SPDB sub 1 and SPDB 2 and 3. So this is for the feeder 1 fabrication line. So this is for the feeder 2 assembly line, and the last one is painting line for the feeder 3. Okay, so basically the voltage drop from the TNB is below 99.99, which is below than 10%. Also the at SPDB below than 10%, which is 99.92.2. So from the SPDB 2 and 3 is 99.72%. So at the feeder 1, which is 98.35%. So for the feeder 3, which is 98.78%. So basically all the voltage drop which is below than 10%. So we proceed to the fault analysis. Okay, first of all, I apply the fault at the load at the feeder 1. So basically, if we put the fault at the load, single load, only just one circuit breaker will open, which is CB58 just open. So next I will apply the fault at bus bar 1, which is fabrication. So I will put the fault at here. So basically, if we put the fault at the bus bar here, which is here, so we have four circuit breaker will open, which is CB15, CB16, 58, and the last one is 12. CB4 not open because we just set the motor spare. So basically, all the fault was successfully done. Okay, now the last step is I will show you the design issues and the solution. Okay, so here the design issues is if the TNB was breakdown, which is no supply from TNB for the factory, all the load from the factory will be breakdown too, and do not have any voltage or supply to generate the load. So my group was thinking how to get the solution, how to as a backup solution. We think we need to put 3 generator for 3 feeder, which is feeder 1, feeder 2, and feeder 3. So basically what you can see here, open skip this for the open skip breaker, and also this open, and this open, which is this 3 is the backup supply, which is generator. Okay, if I open skip for the 3 skip breaker, you can see. So we can see no supply from at the feeder 1. Same goes to feeder 3. Also no supply from the TNB. And feeder 2. So the solution for that, we put the generator as a backup supply. So this will be turned on. What we can see here, the supply will start. So we can see here the flow analysis. This is the red one. And also I applied for the backup supply too, for the feeder 3. And the last one is for the feeder 2. So you can see here, all the load will be back normally to supply to produce the product. So for proof, the generator backup supply 1, 2 and 3 we use a generator as a backup plan and the solution for design issues to produce the backup supply for the factory. So that's all from me, Doctor. Thank you.
Hi, my name is Muhammad Hafiz bin Rusli, DE180159. So now I will explain about the load flow analysis for this project. So this table shows the result for the upper distribution part. So the upper distribution part consists of from the technical supply to the transformer 1 and transformer 2. So from the simulation, the real power obtained is around 2.22 megawatt. In contrast, the apparent power is 1.05 megawatt. So the value is quite big as it was in the upper part of the electrical distribution. So the reading of the busbar SMGDB is 10.99 kV, which has a drop voltage around 0.09% only. So this considered a good design as the voltage drop percentage is less than 10%. Okay, moving on to the reading of the SPDB 1, 2 and 3. So the voltage reading for the SPDB 1 and 2 still 11 kV, but for the SPDB 3 is dropped into 3.3 kV because of the step down transformer from 11 kV to the 3.3 kV. So the measured voltage at the busbar SPDB 1 and 2 and 3 is 10.9 kV, 10.96 kV and 3.26 kV respectively. So both voltage drop at the busbar SPDB 1 and 2 is less than 1%, while the voltage drop at the busbar SPDB 3 is 1.33% only. So this is a table for the fabrication line. So the fabrication line is the heaviest load being placed. The primary load such as a process compressor is rated at 6.6 kV. So the voltage supply for the busbar feeder 1 is coming from the SPDB 1, which is stepped down from 11 kV to 6.6 kV. The measured voltage at the busbar feeder 1 is 6.49 kV, which has a 1.67% difference from the rated voltage. In the busbar feeder 1, the line at the cable 11 and 13 has the highest wattage consumed, which is 807,875 watt, then 86,812 watt at the cable 14 for LV load 1. The line at the cable 12 doesn't consume any power as the process compressor B was put in the standby mode. The voltage as at the busbar LV is rated at 0.41 kV. It is then dropped to 0.402 kV due to a few reasons such as the resistance in the cable or the type of load itself. Okay, continue to the S parameter on the assembly line, which is recorded at feeder 2, SPDB line, busbar and the LV load 2. The voltage rating is stepped down from 11 kV to 0.415 kV by using step down transformer. So the real power measured at the feeder 2 120,106 watt, which is higher than the LV load 121,748 watt. While for the apparent power, LV load 2 and feeder 2 obtained 82,568 var and 81,519 var respectively. Hence, the measured voltage at the LV busbar obtained 0.410 kV along with 1.21% of voltage drop percentage. Okay, lastly, the parameter on the Pantene line, which is the last line in this car manufacturing company. So the voltage rating for all load is 3.3 kV except at the SPDB busbar LV2 and LV load 3 network, which is rated at 0.415 kV. Then both treated water pump A and process compressor C obtain the same apparent power, 67,665 var, while the measured voltage at the busbar feeder 3 is 3.26 kV along with the percentage of voltage drop of 1.21%. This same goes for the measured voltage and the voltage drop percentage of the DB process for the both treated water pump A and pump C. Okay, last but not least, the SPDB fabrication line busbar LV2 bring along 2.17% of voltage drop with 0.4006 kV measured voltage.
Assalamualaikum. My name is Nur Azrini bin Azhar. My measure number is DE180152. Okay, so let me proceed for the fault analysis result. Which is this section is highlighted the procedure of identifying electrical faults in the car manufacturing process. Okay, so what is an electrical fault? An electrical fault is an unexpected conditions, which is it may cause of incorrectly operational. So as you may see here, the fault is applied in the fabrication line, which is feeder 1, and the protection at relay 40 may detect the fault at cable 11, which is after the relay location, and then the circuit breaker, which is with the cross shape here, is tripped with a time delay. So this is how the fault occur at the DB bus bar, which is the distribution board bus bar. Okay, for the next part, okay, I'll proceed with the result fault at SPDB, which is the subprime distribution board. So this is, as you may see, the fault occur is at the end of the bus bar, and relay 44 will detect the fault, and CB12 will be tripped, and the whole circuit breaker 2, 5, 6 and 7 will be in open condition. So it may also act as a backup in case the protection of an outgoing feeders is failing. Okay, for the last part is parameters before and after faults occur. So as you may see here, there are some differences about that. So the current at bus bar for the without fault presence is 171.8 kiloampere, while for the fault at process compressor A is 2.273, and lastly for the fault at bus bar, the current will be 2.286 kiloampere. So you may see it differs specifically. So for the next part is the current at process compressor A without fault at presence is 77.2 kiloamp, and for the current at process compressor B is 7.7 kiloamp, and the current at process compressor C, which is without any fault presence, is 77.2. And last but not least is the voltage at bus bar in kilovolt, which is from the without fault presence is 6.49 kilovolt, while for the fault occurred is 3.68 and 3.71 respectively. So the voltage drop is quite high, something like almost to 50%. So that's all from me. Thank you.
My name is Muhammad Aziz Aswad bin Sham and my matric number is DE180187. Okay, now I will explain about the conclusion. Okay, at the end of this project, students know how to design a proper network design for the installation segment that includes expected power consumption and overall power factor demand by using Microsoft Excel. And this Microsoft Excel will make the job easier by allowing users to shorten the time used for endless calculation of expected power consumption and overall power factor demand. Besides, students also learn on how to create the single line diagram for an industrial installation that indicate the mains, distribution transformer, and using the suitable installation procedure. After that, students also learn on how to sketch the industrial power network by using the ETAP software. These projects are very useful for industrial and power supplier. Then, by use this software, and they did not need any external document to be processed. Okay, for the weaknesses is, after completing this project, we can say that there could be some technical issue might happen in the system, such as electrical issues. Okay, this is due to the software implementation did not take the worst case scenario. The design might be different if it was put up in the real life. There are some effective ways to solve this problem. Okay, firstly, like example, do maintenance frequently in order to observe the system whether that the system is good or needs some improvement in the software. Okay, that's all from us. Thank you.